Hello friends, let us learn about the vibrations in polyatomic molecules in this module. After studying this module, you shall be able to understand the concept of degrees of freedom and fundamental vibrations in a molecule, learn about skeletal vibrations and group vibrations, learn about vibrational spectra of few polyatomic molecules like water and carbon dioxide. Let us begin with the introduction. In the last few modules, we have studied about the vibrational spectra of diatomic molecule executing harmonic motion as well as anharmonic motion. We also learned the joint vibration rotation spectra of a diatomic molecule observed under high resolution. In this molecule, we shall discuss how vibrational spectra of polyatomic molecules looks like. For this, we need to know the concept of degrees of freedom of a molecule. Degrees of freedom of a molecule are defined as the number of coordinates that are required to specify the position of each and every atom in a molecule. For any molecule, if n is the total number of atoms present, the total degrees of freedom of the molecule will be given by 3n. This means that a total of 3n coordinates will be required to specify the position of each and every atom in that molecule. According to the kinetic theory of matter, when a molecule absorbs thermal energy, it executes three different types of motion in the following manner. Number one is the translational motion. In this motion, the molecule moves as a whole and is described by the movement of its center of mass. Since any point in the space can be described by specifying three coordinates, the total number of translational degrees of freedom for any molecule will be 3. Number 2 is the rotational motion. In this motion, the molecule rotates about an axis passing through its center of gravity and perpendicular to the plane of rotation. For any molecule, there are 3 permitted modes of motion, that is, rotation about the major symmetry axis, moment of inertia associated is IA, n over n rotation in plane, moment of inertia associated is IB, and n over n rotation perpendicular to the plane, moment of inertia associated is IC. A linear molecule can rotate around 2 mutually perpendicular axes and is thus associated with 2 rotational degrees of freedom. On the other hand, any non-linear molecule can rotate about 3 mutually perpendicular axes and is thus associated with 3 rotational degrees of freedom. Number 3 is the vibrational motion. In this motion, the molecule undergoes to and fro motion about its mean equilibrium position. For any molecule, there are 3 permitted modes of vibration, viz. Symmetric stretching, asymmetric stretching and the bending mode. Out of the total 3n degrees of freedom, a linear molecule will have 3n minus 5 vibrational degrees of freedom, whereas a non-linear molecule will have 3n minus 6 vibrational degrees of freedom. A molecule with n atoms will have a total of n minus 1 bonds between its atoms, and therefore it will have n minus 1 stretching modes of vibration. During a stretching mode, it is the bond length of the molecule that changes. In the bending mode, on the other hand, there occurs a change in the bond angle between the atoms of a molecule. For a linear molecule, there are a total of 3n minus 5 vibrational degrees of freedom, out of which n minus 1 are the stretching modes. The remaining therefore are 2n minus 4 bending modes of vibration. For a non-linear molecule, there are a total of 3n minus 6 vibrational degrees of freedom, out of which n minus 1 are the stretching modes. The remaining therefore are 2n minus 5 bending modes of vibration. It is to be noted that bending mode appears at a lower wave number or frequency as compared to symmetric stretching or asymmetric stretching modes. This is because lesser force is required to bend a molecule as compared to stretch a molecule. The bending mode is therefore associated with a lower force constant and hence a lower vibrational frequency. Now let us look at a question. Find out the total number of vibrational degrees of freedom, number of stretching modes and bending modes for the following molecules. Number A is oxygen, B is HCl, C carbon dioxide, 3 is water and E is acetylene. Now let us look at the solution. For oxygen molecule, it is a homonuclear diatomic molecule with the total number of atoms N is equals to 2. The total number of degrees of freedom is equals to 3N, which is equals to 6. Translational degrees of freedom will be equals to 3. Rotational degrees of freedom will be equals to 2 because it's a linear molecule, and therefore the vibrational degrees of freedom will be equals to 3n minus 5 equals to 1, which will be associated with symmetric stretching. Number of stretching modes will be n minus 1, which will be equals to 1, and number of bending modes would be 2n minus 4, which come out to be 0. For HCl, that is the hydrogen chloride molecule, it is a heteronuclear diatomic molecule with total number of atoms N is equals to 2. Total number of degrees of freedom is 3n equals to 6. Translational degrees of freedom will be 3. Rotational degrees of freedom will be 2 because it's a linear molecule, and therefore vibrational degrees of freedom will be 3n minus 5 equals to 1, again which is associated with the symmetric stretching. Number of stretching modes is equals to n minus 1 equals to 1, and number of bending modes would be 2n minus 4 equals to 0. Number 3 is the carbon dioxide molecule. It is a linear triatomic molecule with total number of atoms N is equals to 3. Total number of degrees of freedom will be 3n equals to 9. Translational degrees of freedom will be 3. Rotational degrees of freedom are 2, again since it's a linear molecule. Therefore, vibrational degrees of freedom will be 3n minus 5 equals to 4. Number of stretching modes will be n minus 1, which is 2. That means corresponding to the symmetric stretching and the asymmetric stretching modes. Number of bending modes will be 2n minus 4, which is equals to 2, corresponding to 2 degenerate bending modes. Now, next molecule is water. It is a non-linear triatomic molecule with total number of atoms N is equals to 3. Total number of degrees of freedom is 3n equals to 9. Rotational degrees of freedom will be 3 because it's a non-linear molecule. Therefore, the vibrational degrees of freedom will be 3n minus 6 equals to 3. The number of stretching modes will be n minus 1 equals to 2, giving symmetric stretching and the asymmetric stretching modes, and the number of bending modes will be equals to 2n minus 5 equals to 1. Now let us look at the acetylene molecule. It is a linear tetraatomic molecule with total number of atoms N being equals to 4. Total number of degrees of freedom will be 3n, which is 12. Translational degrees of freedom will be 3. Rotational degrees of freedom will be 2 because again it's a linear molecule, and therefore the vibrational degrees of freedom will be 3n minus 5, which comes out to be 7. Number of stretching modes will be equals to n minus 1, which will be equals to 3, corresponding to 2 symmetric stretching modes and 1 asymmetric stretching mode, and the number of bending modes will be equals to 2n minus 4, which come out to be 4, that is 2 doubly degenerate bending modes. We have now learnt about the number of vibrational modes that are possible in any molecule. These vibrations can be broadly classified into two categories as skeletal vibrations and the group vibrations. Skeletal vibrations. These vibrations involve all the constituent atoms of a molecule and are observed below 1500 centimeter inverse. They help in establishing the general structure of a molecule such as linear, branched, benzenoid, quinonoid, etc. These vibrations are characteristic of any molecule, and therefore the region below 1500 cm inverse where these bands are observed is called as the fingerprint region. Just as no two fingerprints can be alike, in the similar manner, no two molecules will absorb at the same wave number and have the same IR spectra. This method is very useful in confirming the structure of any molecule by comparing its vibrational spectra to a known standard. Let us learn about the group vibrations. These vibrations involve a particular functional group or any characteristic group present in a molecule. They are usually not related to the structure of a molecule and are generally observed above 1500 cm inverse. For example, the fundamental absorption frequency for a stretching mode in a carbonyl group is observed between 1760 to 1690 cm inverse. Stretching in a hydrogen bonding hydroxyl group is observed between 3400 to 3200 cm inverse, and so on. There are few exceptions, however, like CCl stretching is observed between 800 to 700 cm inverse. The frequency of absorption, that is nu C bar, for any group is given by nu C bar is equals to 1 by 2 pi C under root k by mu, as shown by equation 1 here, where c is the speed of the light equals to 2.9999 × 10 to the power 8 meters per second, k is the force constant, and mu is the reduced mass of the group. For example, if we consider single bond, double bond and a triple bond, the force constants for these bonds vary as k for the triple bond will be greater than the k for the double bond, which will be greater than the k for the single bond. And therefore, the group frequency will be in the order nu C bar will be highest for the triple bond, then for the double bond, and the least for the single bond. Another example is if we consider the group CX, where X can be H, F, Cl or Br. The reduced mass varies in the order as shown, that is mu for CH is smaller than mu for CF bond, than mu for CCl bond, and mu for CBr. And therefore, the group frequency will vary as nu C bar will be highest for CH, and after that for CF, followed by CCl and CBr in the order. Now let us look at the vibrational spectra of one of the very important molecules, that is water. Having learnt about the different vibrational modes of motion and the different types of vibrations in a molecule, let us look at the vibrational spectra of an important polyatomic molecule, namely water. Water is a non-linear triatomic polar molecule. Since the total number of atoms N are 3, there will be a total of 9 degrees of freedom. Out of these 9 degrees of freedom, 3 are translational degrees of freedom, 3 are rotational degrees of freedom, and the remaining 3 are the vibrational degrees of freedom. The 3 vibrational modes of motion are called as the normal modes of vibration. The latter is a type of a molecular motion in which all the atoms in a molecule are vibrating with the same frequency and also pass through their equilibrium positions simultaneously. We know that the essential criteria for a molecule to show vibrational activity is that dipole moment of the molecule must change vis-a-vis a particular mode of vibration. This change in the dipole moment can take place either parallel or perpendicular to the axis of symmetry. In water, C2 axis is the major symmetry axis. That is, if we rotate the molecule by 360 by 2, that is 180 degrees, we get the identical molecule as shown in the following video. Figure 1 shows the C2 axis of symmetry in water. Figure 2 shows the different modes of vibration in a water molecule. In the symmetric stretch, if we rotate the vibrating molecule by 180 degrees, the vibrations remain unchanged. Hence, this is called the symmetric stretching mode, in which the dipole moment changes parallel to the C2 axis of symmetry. This mode is therefore IR active. The wave number for stretching mode of vibration is represented by nu1 bar. The bending mode is also symmetric, in which the dipole moment changes parallel to the C2 axis. Hence, this mode is also IR active. The wave number for bending mode of vibration is represented as nu2 bar. However, in the asymmetric stretching mode, if we rotate the molecule about the C2 axis of symmetry, the vibration produced are anti-phase with the original vibrations. Therefore, this is called an asymmetric stretching mode, in which the dipole moment changes perpendicular to the C2 axis of symmetry. This mode is also IR active. The wave number for asymmetric stretching mode is represented by nu3 bar. Figure 2 shows the vibrational modes of motion in water. This is depicted in the following video as well. Thus, all three vibration modes of motion of water are IR active. Their wave number are in the following order. Bending mode is around 1595 cm inverse and it is the lowest in the wave number, followed by symmetric stretching mode, which occurs at 3657 cm inverse, and followed by the asymmetric mode, which occurs at the highest wave number around 3756 cm inverse. If we assume that the molecule behaves as an anharmonic oscillator, the total energy of the molecule will be given by equation 2 as E bar total will be given by V1 plus half nu1 bar minus V1 plus half square nu1 bar x1 plus V2 plus half nu2 bar minus V2 plus half whole square nu2 bar x2 plus V3 plus half nu3 bar minus V3 plus half whole square nu3 bar x3, where V1, V2 and V3 are the vibrational quantum numbers for the symmetric stretching, bending and the asymmetric stretching modes respectively. Nu1 bar, nu2 bar and nu3 bar are the fundamental vibrational frequencies for the symmetric stretching, bending and the asymmetric stretching modes respectively, and x1, x2 and x3 are the anharmonicity constants for symmetric stretching, bending and the asymmetric stretching modes respectively. The selection rules for the three modes of vibration will be given by delta V1, delta V2 and delta V3 can be equals to plus minus 1, plus minus 2, plus minus 3 and so on, where V1, V2 and V3 are the vibrational quantum numbers for symmetric stretching, bending and the asymmetric stretching modes respectively. We see that in principle all transitions are allowed, but we know that at the room temperature the population of the ground vibrational state corresponding to V equals to 0 is maximum and it decreases sharply with the increase in the vibrational energy level. Therefore, we will observe three fundamental transitions at nu1 bar 1 minus 2x1, nu2 bar 1 minus 2x2 and nu3 bar 1 minus 2x3 for the symmetric stretching, bending and the asymmetric stretching modes respectively. A water molecule therefore absorbs very strongly in the IR region. The fundamental transitions will be flanked by overtones of weak intensity. Certain combination as well as the different bands are also observed, which make the analysis of the spectra complex. They have been discussed in detail later. Now, let us look at the vibrational spectra of carbon dioxide molecule. Carbon dioxide is a linear triatomic nonpolar molecule. Since the total number of atoms N are 3, there will be a total of 9 degrees of freedom. Out of these 9 degrees of freedom, 3 are translational degrees of freedom, 2 are the rotational degrees of freedom being a linear molecule, and the remaining 4 are the vibrational degrees of freedom. Amongst the 4 vibrational degrees of freedom, 1 is the symmetric stretching mode, 1 is an asymmetric stretching mode and 2 are the degenerate bending modes. In carbon dioxide, there are 2 different types of symmetry axes. There are infinite number of two-fold axes of rotation, that is C2 axis of symmetry, which are perpendicular to the CO2 bond axis, and there is also a C infinity axis of symmetry which passes through the CO2 bond axis. This C infinity axis is the major axis of symmetry in carbon dioxide. Figure 3 shows the different modes of vibration in the carbon dioxide molecule. In the symmetric stretching mode, the dipole moment changes parallel to the C infinity, that is the major axis of symmetry. But overall, the change in the dipole moment of the molecule is 0. This mode is therefore IR inactive. In the asymmetric stretching mode, the dipole moment again changes parallel to the major axis of symmetry. This mode is IR active and appears at 2349.3 cm inverse, that is our nu3 bar. In the bending mode, however, the change in the dipole moment occurs perpendicular to the major axis of symmetry. This mode is also IR active and is observed at 667.3 cm inverse as shown by nu2 bar. Thus, only two vibrational modes of motion of carbon dioxide, that is the bending mode and the asymmetric stretching mode, are IR active. Their wave numbers are in the following order. Bending mode occurs at 667.3 cm inverse, occurs at a lower wave number compared to the asymmetric stretch that occurs around 2349.3 cm inverse. Figure 3 depicts the vibrational modes of motion in carbon dioxide molecule. This has been shown in the following video as well. Figure 4 shows the vibrational spectrum of carbon dioxide observed under low resolution. We observe only two fundamental transitions at nu2 bar 1-2x2 and nu3 bar 1-2x3 for the bending mode and asymmetric stretching modes respectively. This is because the symmetric stretching mode is IR inactive, as there occurs no change in the dipole moment. The fundamental transitions will be flanked by the overtones of weak intensity. Figure 4 shows the vibrational spectrum of carbon dioxide molecule. Degrees of freedom of a molecule are defined as the number of coordinates that are required to specify the position of each and every atom in a molecule. For any molecule, if n is the total number of atoms present, the total degrees of freedom of the molecule will be given by 3n. Out of the total 3n degrees of freedom, a linear molecule will have 3n minus 5 vibrational degrees of freedom, whereas a non-linear molecule will have 3n minus 6 vibration degrees of freedom. For a linear molecule, there will be n minus 1 stretching modes and 2n minus 4 bending modes of vibration. On the other hand, for a non-linear molecule, there will be n minus 1 stretching modes and 2n minus 5 bending modes of vibration. The bending mode appears at a lower wave number of frequency as compared to the symmetric stretching or the asymmetric stretching modes. This is because lesser force is required to bend a molecule as compared to stretch a molecule. The vibrations in any molecule can be broadly classified into two categories as the skeletal vibrations and the group vibrations. Skeletal vibrations involve all the constituent atoms of a molecule and are generally observed below 1500 cm inverse. They help in establishing the general structure of a molecule. Group vibrations involve a particular functional group or any characteristic group present in the molecule. They are usually not related to the structure of a molecule and are generally observed above 1500 cm inverse. Water absorbs strongly in the IR region and shows three fundamental transitions at nu1 bar 1-2x1, nu2 bar 1-2x2 and at nu3 bar 1-2x3 corresponding to the symmetric stretching, bending and the asymmetric stretching modes respectively. The fundamental transitions will be flanked by overtones of weak intensity. Certain combination and different bands also observed which make the analysis of the spectra complex. Vibration spectrum of carbon dioxide under low resolution consists of only two fundamental transitions at nu2 bar into 1-2x2 and nu3 bar into 1-2x3 for bending mode and the asymmetric stretching modes respectively. The symmetric stretching mode is IR inactive as there occurs no change in the dipole moment. The fundamental transitions will be flanked by overtones of weak intensity.